As I alluded to in a previous video, there are several different kinds of geometries that we can consider that are broadly broken up into Euclidean and non-Euclidean geometries. The Euclidean geometry is the one that we're most familiar with, but the non-Euclidean geometries also have very important theoretical and practical applications. As it turns out, the main thing that distinguishes between Euclidean and non-Euclidean geometries has to do with parallel lines. So before we start talking about the differences between the various geometries that we're looking at, we're going to establish some facts about parallel lines that apply in all cases that aren't dependent on what kind of geometry we're looking at. So let's start with a definition. Definition 65 says that if L and L prime are coplanar lines and L intersect L prime is empty, that is, there are no points in common between the lines L and L prime, then L and L prime are parallel, and we write that L is parallel to L prime. All right, so this is our standard definition of parallel lines. It's just two lines that don't intersect, although we do specify here they have to be coplanar. If we have two lines that don't intersect that aren't coplanar, that is, they just go off in completely separate directions, don't lie in a single plane, the term for that is skew lines, S-K-E-W, though we won't be using that terminology much. We're mostly going to be interested in geometry that happens within a single plane, as the title of this section suggests. So we've got a notion of parallel lines, and a lot of what we're going to be working on today is talking about what we can conclude when we have parallel lines and how we can know when two lines are parallel. And the first result along these lines is Theorem 66, which says that if two coplanar lines, L and L prime, are each perpendicular to a third line, L double prime, then L is parallel to L prime. Let's look at the picture of this to see why this makes sense. So the picture that we have here is we've got a couple of lines, L and L prime, and we're told that they are each perpendicular to this line, L double prime. Very often, when we're trying to prove that two lines are parallel, we do this by contradiction. We assume that there is some point that is not, or that rather that is on both lines, that i.e. that the two lines are not parallel, and try to come up with a contradiction. This is actually similar to a result that we had earlier, which we can use. So, to prove this by contradiction, we're going to assume that they are not parallel. So, assume for contradiction that P lies in L intersect L prime. Now we have to consider two possibilities. What if P actually lies on L double prime, and what if P doesn't lie on L double prime? Let's just consider the case that P does not lie on L double prime. If that's the case, then we have a picture like this. And of course, the way that we draw it is going to look wrong, but that's because we're doing a proof by contradiction. We're going to try and show why the picture that we've drawn can't happen, can't work. And so what we have here is the line L double prime, and then we've got two lines L and L prime that are both perpendicular to L double prime that pass through the point P. But we've actually already shown that this can't happen. Let's see, it was Theorem 59. No, I'm sorry. Corollary 57. Then by Corollary 57, there is a unique line through P and perpendicular to L double prime, which is a contradiction. So we show that in this situation, we have two lines that go through P and are both perpendicular to the line L double prime. That's exactly the sort of thing that Corollary 57 says can't happen. And then the case where P actually does lie on L prime, we won't go through this, we won't write this down explicitly, but in this case, we'd have some sort of picture like this, where we've got L and L prime. And the issue here is that we've got the two lines L and L prime that are each forming an angle of 90 degrees with the line L double prime at P. And we know that can't happen because the angle construction axiom, the angle construction postulate says that there is a unique line, or a unique ray forming a given angle with a ray that lies in a specified plane. So Theorem 66 says that one way of showing that two lines are parallel is to show that they're each perpendicular to a third line. Along similar lines here, we have the following. Theorem 67, which says that basically parallel lines always exist. Given a line L and point P not in L, there exists a line L prime such that P lies in L prime and L is parallel to L prime. The proof of this is an exercise. The sketch of the situation helps to see how the proof might go. We've got a line L and a point P. We want to show that there's some line that goes through P that is parallel to L. And what we're going to want to do is to use the previous result, Theorem 66. So if you can somehow construct a line here, this blue line, in such a way that it's perpendicular to L, and then construct a line that goes through P that's perpendicular to that one, well then Theorem 66 will tell you that the green line is perpendicular to, or is parallel rather, to L, which is what we wanted. This sort of situation where we've got a couple of lines, the green and the white, and a line that passes through both of them, comes up very often in the types of arguments that we're about to start working on, and so we want to give it some terminology. So definition 68. If L, L prime, and M are coplanar lines, and L and L prime each intersect M in different points, P and Q, respectively, then M is called a transversal of L and L prime. So the picture we have is something like this, where we got M, L, L prime, and this M here is the transversal. We got P and Q. Now, let me give some other points on this diagram in order to say the next part of it. Let's let A and B be here, C and D be here, such that A and C are on the same side of the line M. And let's see, I also want P, Q, R over here. R is the point on the line M. All right, so in this situation, we have that the angle APQ and the angle DQP are alternate interior angles. And angle APQ and angle CQR are called corresponding angles. So the alternate interior angles are like the red ones here. They are both between the two lines, L and L prime, sort of, and they are on opposite sides of the line M. Of course, there are other pairs of alternate interior angles, or one other pair of alternate interior angles here, BPQ and CQP. But we also have corresponding angles, and we have 4 pairs of corresponding angles. So the angle here at A corresponds to the angle here. And again, looking at the picture, the idea is that the lower left angles in both intersections are called corresponding, and similarly the upper right angles in both cases would be called corresponding. So there are 2 pairs of alternate interior angles and 4 pairs of corresponding angles. And how these angles interact with each other is very important when it comes to talking about the lines L and L prime being parallel to one another. And the main theorem that we have is, with regards to this, is the next one. Theorem 69 says that if M is a transversal of L and L prime and a pair of alternating interior angles are congruent, or a pair of corresponding angles are congruent, then L is parallel to L prime. So let's sketch out this situation here. We've got M, which is a transversal to L and L prime. And this theorem is telling us that if a pair of alternate interior angles, I wrote alternating, I shouldn't have done that, alternate. If a pair of alternate interior angles are congruent, then the two lines L and L prime are parallel. Once again, the trick to this, the strategy to this, I should say, is to assume that they're not. Assume that they actually do intersect somewhere over here. Now, if we do that, let me give some names to some of these points. If we do that, then notice that we have a triangle PQR. It doesn't look like a triangle, of course, because I've had to curve the lines to make our impossible situation happen on the page. PQR is a triangle. And once we recognize PQR as a triangle, then the two red angles have a relationship. The red angle at Q is an exterior angle to the triangle PQR, and the red angle at P is a remote interior angle of the red angle at Q. And therefore, we have a theorem on exterior angles, it might even be called the exterior angle theorem, it is, that will tell us that there's a problem with this. Will tell us that the situation that we've drawn here just can't happen. So that'll be the argument for the alternate interior angle case. And then if we have the corresponding angles being congruent to each other, well, we'll just reduce that back to the situation with alternate interior because now the two red angles at P are congruent because they are vertical angles. So this is the strategy for proving Theorem 69. The proof of this one is also an exercise. One of the most difficult parts of setting up this proof is actually just setting up the notation so that you can talk about all these things. So for instance, to talk about all these various angles, you need to give yourselves some more points here, like maybe this will be point A. Let's see, we'll need a point B over here, and I think we'll need a point C down here. We need at least all those points to talk about all the red angles that we're doing here. So your proof would have to start off with something like let P be in, at least the way I've written it here, L prime intersect M. Let Q be in L intersect M. Now, because L prime and M are two different lines, there's only one point in their intersection. And similarly for Q being in L intersect M. Then we could say, assume for contradiction that R lies in L intersect L prime. And then we could say, let A be on the other side of Q from R, B be on the other side of P from R, and we want to express it this way using our betweenness conditions because those are precise. So let Q lie between A and R, B lie between P and R, and P lie between Q and C. So this defines points A, B, and C, and from there you can go ahead and make your argument. You could talk about triangles, exterior angles, and so forth. All right, well, with parallel lines and knowing about parallel lines and perpendicular lines, things like this, we can come to our new topic, which is Sacari Quadrilaterals. One of the many unintuitive things about non-Euclidean geometry is that many of the types of figures and polygons that we take for granted don't actually exist in non-Euclidean geometry. In particular, it's going to turn out that the existence of rectangles, that is a polygon, a quadrilateral containing 4 right angles, doesn't always happen. Not all of our geometries will include rectangles. And we'll talk a little bit more about the history of Euclidean and non-Euclidean geometry in a little bit. But there was a mathematician called Saccheri who was trying to prove that rectangles always exist in all geometries. It turns out he was barking up the wrong tree, but his techniques were very helpful for understanding geometry when we got a better view of what was actually going on. So the idea behind a Secari quadrilateral is we want to try to construct a rectangle, and we're going to be very, very careful about that. We're not going to make any sort of assumptions about how things work. We're just going to use the facts that we already know about the types of constructions that we can make. So if we wanted to build a rectangle, one way of going about it, or the way Saccheri went about it, is the following. Let's start with a line segment here. I'll call that line segment the line segment AD. And then what I want to do is to draw a couple of line segments up from that. And these line segments are both going to be perpendicular to the line containing AD, the segment AD. So we've started building our rectangle. We know from the geometry we're used to that when we have a rectangle, opposite sides are going to be congruent, so we could go ahead and construct our segments that way and give ourselves points BC like this. All right, everything seems fine so far, and then we can look at the segment connecting B and C. What we can't assume at this point, and can't even prove at this point based on what we have, is that the angles at B and C are right angles. We don't know that they're right angles, and in fact, they aren't always right angles, depending on your geometry. But this is a Secari quadrilateral. Let's give the formal definition based on this. Definition 70. The quadrilateral ABCD is a Saccheri quadrilateral if first the angle at A and the angle at D are right angles. The segment AB is congruent to the segment CD. And 3, B and C are on the same side of the line AD. This part 3 here is sort of a partial part of the definition of what it means to be a convex quadrilateral. As it turns out, the other conditions in the definition of Secari quadrilateral do guarantee that all Secari quadrilaterals are convex quadrilaterals, but the basic assumption just gives that B and C are on the same side of AD, which is the sort of thing that you would use when constructing such such a quadrilateral. Now some terminology that we're going to use a lot. The segment AD is called the lower base, and the segment BC is called the upper base. Of course, Secari quadrilaterals can be oriented however you want, but most often they're oriented the way that we've drawn it here, hence the name lower base and upper base. And similarly, the angles, angle B and angle C, are called the upper base angles. So here's our Saccheri Quadrilateral. We can label it. We've got our lower base, our upper base, and our upper base angles. And what Saccheri was trying to prove is that if you make a construction like this, then the upper base angles have to be right angles. Unfortunately, this is not the case. They can be non-right angles in some cases. Nevertheless, Secari Quadrilaterals have sufficient structure to them that there are lots of things that we can say about them, lots of nice symmetrical things that they have. So for instance, we have theorem 71, which is sort of a congruence statement for Secari Quadrilaterals, even though we haven't defined congruence of figures other than triangles. So theorem 71, if triangle ABCD and triangle A prime, B prime, C prime, D prime are Secari, which is just short for saying they're Secari Quadrilaterals. And we should specify their lower bases, AD and A prime, D prime. If we have two Secari Quadrilaterals and we know the following, if we know that their lower bases are congruent segments, and we know that one of their corresponding sides are congruent, AB is congruent to A prime, B prime, then we have congruence of all the other pieces in the Secari Quadrilateral. So if all those things are true, then we can conclude that BC is congruent to B prime, C prime. The angle at B is congruent to the angle at B prime, and the angle at C is congruent to the angle at C prime. So let's sketch out a couple of Secari Quadrilaterals, work through the proof. All right, so we've got A, D, A prime, D prime, and B, C, B prime, C prime. And let's see, what are we told? We are told that AD is congruent to A prime, D prime. We're told that AB is congruent to A prime, B prime. Now, of course, some of the results that we have here we get for free. So since quadrilateral ABCD and quadrilateral A prime, B prime, C prime, D prime are Secari, we have that the segment CD is congruent to the segment AB. That's part of the definition of being a Secari quadrilateral. our hypothesis, one of our hypotheses, is that the segment AB is congruent to the segment A prime B prime. And because the second quadrilateral is Saccheri, that means that segment A prime B prime is congruent to segment C prime D prime. So that gives us part of what we're going to use here. So now we want to get up to talking about BC and B prime C prime. So what we want to do is we want to construct a couple of triangles here. Let's see what happens when we construct the triangle by connecting B to D and B prime to D prime. Now notice that the triangles ABD and A prime B prime D prime have a congruent pair of angles, they're right angle there, and they have congruent legs. AB is congruent to A prime B prime, AD is congruent to A prime D prime, and therefore we can use side angle side. So by side angle side, triangle ABD is congruent to triangle A prime, B prime, D prime. And so in particular, that means that we can get that these two diagonals are congruent. So that means pardon me. Oh, sorry. I want to go further. These two triangles, though, are also congruent to the triangles that we get going the other way. Sorry, I forgot that we wanted to put in the other two diagonals as well. So these other blue lines are also going to be congruent there by side angle side again. So if we look at A prime, B prime, D prime and compare that to triangle D prime, C prime, A prime, and all of those are going to be congruent again to D, C, A. So we have four different congruent triangles here by side angle side. And now let's take advantage of this. So we have that C is in the interior of angle BAD. Now, we need to be careful about this. Anytime we say that a point is in the interior of some angle, we need to make sure that we have some sort of justification for that. By definition of the Secari Quadrilateral, B and C are on the same side of the line AD. So that's half of what it means to be in the interior of an angle. The other thing that we need to know is that D and C are on the same side of the line AB. We can get that in the following way, by using perpendicular lines. Since the line AB is perpendicular to the line AD, which is again perpendicular to the line CD, we have that AB is parallel to CD. Now in particular, what that means is that all points of the line CD lie on the same side of the line AB. And this is because there's no possible way for the segment containing 2 points in the line CD to cross the line AB, otherwise the two lines wouldn't be parallel. So therefore, C and D are on the same side of line AB, which is the second part of what we needed for the interior statement. So just restating this, C is in the interior of angle BAD. All right, let's take this information that we have. We've got a bunch of congruent triangles, which I'll write down in a second after I duplicate this over. So let's see, what do we have? We have that triangle ABD is congruent to triangle DCA, which is congruent to triangle A prime B prime D prime, which is congruent to triangle D prime C prime A prime. And we have that C is in the interior of angle BAD, and by similar arguments, we have that B is in the interior of angle CDA, C prime is in the interior of angle B prime A prime D prime, and B prime is in the interior of angle C prime D prime A prime. So we've got a lot of congruences. We know that our sketch is essentially correct in terms of where points lie in the interiors of their opposite angles. And so we can go on from here. So now we have that angle CAD is congruent to angle C prime A prime D prime, and we have, because they are corresponding angles inside congruent triangles, and we have that angle BAD is congruent to angle B prime A prime D prime, and that's just because they're both right angles. So by angle subtraction, we have that the angle BAC is congruent to angle B prime A prime C prime. So we get that the blue angles here are congruent to one another. So now that gives us congruences of the other triangles, of the upper triangles. So that means that triangle ABC is congruent to triangle A prime B prime C prime by side angle side again. And so that means that segment BC is congruent to segment B prime C prime. So that's going to give us the first part of what we were looking for. But it's also going to give us the another part of what we were looking for, because that tells us that the angle ABC is congruent to the angle A prime B prime C prime, which is another thing that we were looking for. So we were trying to get that the upper base angles of the two Sacari quadrilaterals were congruent. So the last thing we need to do is to get the upper base angles at C and C prime to be congruent to one another. We can basically use a similar argument. So by a similar argument, we have that triangle BCD is congruent to triangle B prime C prime D prime. The similar argument being again, that we've got congruent angles ADB and A prime D prime B prime, and then because B and B prime are in the interiors of the angles ADC and A prime D prime C prime, and the angles ADC and A prime D prime C prime are congruent because they're because they are right angles, then we get that the triangles BCD and B prime C prime D prime are congruent, and so we have that the angle BCD is congruent to the angle B prime C prime D prime, and that finishes off that problem. So if we've got two Saccheri quadrilaterals, we know that their lower bases are congruent and then one of their sides are congruent, then pairs of sides are congruent, then we get congruence of basically everything else that we can measure about the two quadrilaterals. All right, so if a Secari quadrilateral were a rectangle, then we would know that the upper base and the lower base were congruent to one another. We're not going to be able to prove that that's the case in general, but we will be able to get a relationship between them. We'll be able to show that the upper base can't be smaller. So theorem 72 says if in a Secari quadrilateral, the upper base is greater than or congruent to the lower base. So it might be congruent, making a rectangle, but it might be longer, but in particular, it's never shorter. So here's the strategy that we're going to take. We're going to really build a whole bunch of Secari quadrilaterals that are basically congruent to one another, or where the relevant pieces that we care about are congruent to one another. And then we're going to use the polygonal inequality. All right, let me jump over here and then at the tops of all those. So what we're going to do is we're going to set up a bunch of Secari quadrilaterals like this. We're going to take our first one, A1, A2, A1, B1, B2, A2, as sort of our starting point. So we're going to start with a Secari quadrilateral like that. These two sides are going to be congruent, and then we're going to build copies of this by building out more points, A2, A3, A4, A5, A6, A7, etc., all up to AN, let's see, AN minus 1 to AN. And we're going to construct these points B3, B4, B5, etc. out here. And the point is that all of these Secari quadrilaterals that we're going to build up here all have a lower base that's congruent to the one over on the left, and all have their sides being congruent to the sides of the leftmost Secari quadrilateral. In particular, that's going to mean that all of the upper bases of these Secari quadrilaterals are going to be congruent to one another. From this, we'll be able to see that the segments that the segment B1, B2 cannot be smaller than the segment A1, A2. But rather than talking about how that's going to happen, let's work through this process. So proof. Let's let quadrilateral A1, A2, B1, B2 be Saccheri with lower base A1, A2. So now let's fix a number n greater than or equal to 3 and let A3, A4 up through AN be points in the line containing A1 and A2 such that a few things. We need to make sure that they all lie in order like this. So in particular, we want to make sure that for all I, we have that AI minus 1 to AI to AI plus 1. So we need to make sure that the betweenness relations, as we've sketched out in the problem here, are all maintained. And we want the segment AI plus 1 to be congruent to A1, the segment A1, A2. So we're just going to keep building points out along the ray A1, A2, making all these things happen. Now, furthermore, let B2, B3 up to Bn be points on the same side of the line A1, A2 as B1 and B2. Oh, we already have B2. We don't need to grab it. We want to take things starting with B3. B3, B4 up to Bn be points on the same side of the line as B1, and with the line AI, BI being perpendicular to the line A1, A2, and the segment AI, BI being congruent to the segment A1, B1. We can do all of this by the angle segment construction theorem. All right, so now each quadrilateral AI, BI, BI plus 1, AI plus 1 is Saccheri. So, by theorem 73, or sorry, not 73, 71, by theorem 71, the segment BI, BI plus 1 is congruent to the segment B1, B2. Because each of these Secari quadrilaterals have congruent lower bases and sides with the Secari quadrilateral A1, B1, B2, A2. So that has justified that our construction here works, and that the congruences we have along the top are accurate. So now, by the polygonal inequality, we have that a1 to an is less than or equal to. Now, with the polygonal inequality, I can now create any string of distances I like. As long as I start at a1, go to something, and finish up with an. So I'm going to say that the distance from a1 to an is certainly less than or equal to the distance from a1 to b1 plus the distance from b1 to b2 plus the distance from b2 to b3 plus etc., up to the distance from bn minus 1 to bn plus the distance from bn to an. I'm saying that if I take the distance from a1 to an, that's got to be less than the distance if I travel all the way around this basically big region here. So now we have that a1an is actually equal to a1a2 plus a2a3 etc., plus an minus 1 an, and that's because we have all the betweenness relationships that we set up before. And all the a points are in a line, and they all run in sequence. A2 is between a1 and a3, a3 is between a2 and a4, and so forth and so on. So that actually means that the distance from a1 to an is exactly equal to this a1 through an distances, these a1 through an distances. But we also know that the distance from, say, a5 to a6 is the same as the distance from a1 to a2. So, in fact, a2, a3 is the same as the distance from a1 to a2. An minus 1 an is the same as the distance from a1 to a2. And so, in fact, all these things together are just n minus 1 times a1, a2. Because there are n minus 1 of these terms in here, n minus 1 of these distances. Now, similarly, we have that b1, b2 plus b2, b3, etc., up to bn minus 1, bn has the property that each of the terms after the first is equal to the first. That's what Theorem 71 tells us, that the upper base of each of these Sacari quadrilaterals are all congruent to one another, and therefore, if I add up all those distances from b1 to b2, b2 to b3, etc., that's just the same thing as taking n minus 1 times b1, b2. And then also we have that bn an is equal to a1 b1. Because the two segments a1 b1 and an bn are congruent. So what this means is that we can replace each of the pieces in our original inequality with their simplified versions. So instead of a1 to an, I will write it as n minus 1 times a1, a2, and that has to be less than or equal to. Now all the b distances together are n minus 1 times b1, b2, and then a1, b1 plus bn, an is just twice a1, b1. So we have this relationship here, which is now a relationship just between the points or the distances that are in the first Secari quadrilateral we considered. Now, if we rearrange this, we have that b1, b2 is greater than or equal to, what I'm going to do is I'm going to subtract 2a1, b1 from both sides, and I'm going to divide both sides by n minus 1. So what we get is that the distance from B1 to B2 is greater than or equal to A1, A2 minus 2A1, B1 over n minus 1. And remember, these are all real numbers now, so we can use all the facts that we know about real numbers. Now, we have been trying to show in this theorem that B1, B2 is greater than or equal to A1, A2. Of course, we don't exactly have that for any fixed n. We have that B1, B2 is greater than or equal to A1, A2 minus some number. However, this argument that we did holds for any n. It holds for any n. And so we can basically make this term on the right as small as we like simply by taking larger and larger n's. So if B1, B2 were less than A1, A2, then for a large enough n, eventually this inequality would fail. So we can say, since this holds for all n, we have that B1, B2 has to be greater than or equal to A1, A2. Because if it were any less, then eventually the expression on the right, A1, A2 minus 2, A1, B1 over n minus 1, would eventually be larger than it. Another way of thinking about this, when if you're familiar with suprema, is that the statement that we got here says that B1, B2 has to be equal to has to be greater than or equal to, rather, the supremum of the expression on the right for all n. But the supremum of the expression on the right for all n is exactly A1, A2. So we achieved what we wanted. We got that B1, B2 is greater than or equal to A1, A2, which tells us that the upper base of a Sacari quadrilateral is never less than the lower base of that Secari quadrilateral. So, as a quick aside, what does this mean that Secari quadrilaterals actually look like? Well, one possibility, of course, is that they actually are true rectangles. We could have a Secari quadrilateral that looks like this. That's perfectly fine. But the other way that Secari quadrilaterals can look, if we're on a non-Euclidean space which looks curved to our eyes, is something like this. So as I said, this looks a little strange to us, but as it turns out, this is a way of visualizing what can happen in non-Euclidean geometries. In non-Euclidean geometries, the lines in the geometry tend to look curved to us. But the whole notion of curved versus straight depends on the geometry that we're using. The reason it looks curved to us is because the geometry that we interact with on a daily basis is Euclidean, or at least approximately Euclidean. And so if we try to look at a non-Euclidean geometry through that, of course it's going to look a little odd. But we can rely on the theorems that we have, on the axioms, and work with that in order to understand how things can be different than our intuition suggests. Okay, so we've got a few more theorems relating to Secari quadrilaterals that wind up being very important to us. In particular, having to do with triangles, which is perhaps surprising that we use something as complex as a Secari quadrilateral to study a triangle, but it turns out to be, again, very useful. So Theorem 73 says that if the triangle ABD has a right angle at A, then the measure of angle B plus the measure of angle D is less than or equal to 90. In particular, angle B and angle D are acute. So the way this works is we're going to start with a triangle ABD with a right angle at A, and we're trying to show that the sum of the two angles B and D is less than or equal to 90. So as the notation here suggests, what we're going to do is we're going to build a Secari quadrilateral out of this, and then use the results that we have on Sacari Quadrilaterals to help solve this. So proof, we want to let C be on the B side of the line AD such that the line DC is perpendicular to the line AD and the segment CD is congruent to the segment AB. Now, that means that quadrilateral ABCD is Saccheri. By side angle side, we have that the triangle ABD is congruent to the triangle DCA. We were doing this earlier, so we can look at the diagonal from A to C and look at the triangle there, and what we have is that the two triangles ABD and DCA are congruent. So in particular, this means that the segments BD and AC are congruent to one another. So now we are going to use the Hinge Theorem, and we're going to look at the angle ABD, which I'll note here in green, and the angle CDB, which I'll note here in blue. So, if angle ABD is greater than angle CDB, then we would have that segment AD is greater than segment BC by the Hinge Theorem. This is a contradiction. This is a contradiction to what we just proved in Theorem 72, that the upper base can't be less than the lower base. So this means that angle ABD is less than or congruent to angle CDB. So therefore, we have that, let me do this here, we have that 90 is equal to the measure of angle ADC, because that's a right angle by construction, which is equal to the measure of angle ADB plus the measure of angle BCD. That's just by angle addition. So ADB and BDC. So we get that 90 is equal to the measure of ADB, the red angle, plus the blue angle, which is greater than or equal to, we have that CDB is greater than or equal to the measure of angle ABD. So we have, the measure of angle BDC, we had that up here, is greater than or equal to the measure of angle ABD. But that's exactly what we were going for. We were trying to show that the angle, that the green angle and the red angle had a total sum of less than 90. So what we did is we showed basically that the green angle had to be less than or equal to the blue angle by comparing the upper and lower bases of the Secari Quadrilateral, and then used angle addition to say, oh, well, since the blue and the red add up to 90, and the green is less than or equal to the blue, the red plus the green must also add up to less than or equal to 90. All right, so this gives us a step towards understanding the sum of the measures of the interior angles of a triangle. So let's go to Theorem 74. We want to prove that the sum of the interior angles of a triangle always adds up to less than or equal to 180. We're actually not going to be able to prove that it equals 180 in general, but Theorem 74 is a necessary step on the way there. It says if the segment AC is a longest side of triangle ABC and D is in the line AC such that the line BD is perpendicular to the line AC, then D has to lie between A and C. This theorem sort of allows us to simplify our arguments. You remember back when we were working on side, 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 and some of the other theorems that we had to, we constructed these lines down from one side of a triangle down to the other side, and we were either trying to show that they were right angles or we assumed that they were right angles, and then we had to consider all the different possibilities. Well, is this point D between A and C, or is it to the left of A or to the right of C, something like this? What this theorem is saying is that as long as AC is a longest side of the triangle, either longer than any of the others or at least as long as any of the others, then when you drop a perpendicular line from B down to the line AC, the point where that line intersects has to lie between A and C, which does make many of the arguments that we do on these types of problems a lot easier. So let's look at this. Let's suppose not. That is, let's suppose that D does not lie between A and C. That means that there are 4 other possibilities, although 2 of them are very similar, and the other 2 of them are also very similar to one another. So, case 1, let's suppose that D actually equals A. Well, in this case, we have that angle BDC, we want BAC is a right triangle with right angle at A, because in this case we're looking at the picture. We're looking at a picture that looks like this: BDC, but D is also A. Angle BAC is a right angle with right angle A. Hence, by Theorem 73, that means that the angle B, for instance, is acute. Hence, that means that angle B is less than angle A, and so this means that the segment AC is less than the segment BC, which is a contradiction. So if D is actually equal to A, then we get this right triangle, which means that AC is no longer the longest side of A, because the hypotenuse of a right triangle is always the longest side. So case 2, suppose D equals C. This is similar to case 1. If that's the case, then we still have a right triangle. The right triangle is at C rather than at A, but the segment AC is still not the longest side, a contradiction. So case 3, let's suppose that A is between D and C. So this picture looks like the following. We've got B, D, A, AC. So now we have the triangle BDC is a right triangle. So, by a similar argument to the above, we have that the segment BC is greater than the segment DC, but the segment DC is greater than the segment AC, because A lies between D and C, which is again a contradiction. Case 4, which is where D is on the other side, is similar. So if D is on the other side of C from A, then again the triangle ABD is the triangle ABD is a right triangle with right angle at D, and the same sort of argument applies, showing that the segment AC is not the longest side. So this Theorem 74 is really just, the proof of it is really just eliminating all other possibilities. D has to lie between A and C because any other possibility gives rise to a contradiction. All right, so now with that, we're finally able to get to our last theorem of the day. which has to do with the interior angles of a triangle. So theorem 75 says that if triangle ABC is a triangle, then the measure of angle A plus the measure of angle B plus the measure of angle C is less than or equal to 180. It could be less, but it can't be more than 180. So proof. Without loss of generality, we may assume that the segment AC is a longest side. This simplifies our argument. We don't have to consider various cases. So we've got A, B, C, and we're going to drop down a point D like we did before. Let's let D be in the line AC such that the line BD is perpendicular to the line AC. By theorem 74, D lies between A and C. In particular, this means that the measure of angle ABC is equal to the measure of angle ABD plus the measure of angle ABD plus the measure of angle DBC. So now we're going to use theorem 73 twice. So by theorem 73, we have the right triangle ABD, and if we look at the two non-right angles in that triangle, their measures have to add up to less than 180. So by theorem 73, the measure of angle A plus the measure of angle ABD is less than or equal to 90. And similarly, if we look at the triangle DBC, we get that the measure of angle B plus the measure of angle C, measure of angle, need to be precise about this, DBC plus the measure of angle C is less than or equal to 90. Therefore, if we want the measure of angle A plus the measure of angle ABC plus the measure of angle C, which is what we're talking about in the statement of the problem, this is equal to the measure of angle A plus, now, as we said before, since D is in the interior of the segment AC, we have that the measure of angle ABC is equal to the measure of angle ABD plus the measure of angle DBC. And then we still have plus the measure of angle C over here. But now, each of these pairs are less than or equal to 90 by theorem 73, as we mentioned above. So this is less than or equal to 90 plus 90, which is 180. So we get not the equality statement that we've seen many, many times before, but the more general bound. The sum of the interior angles of a triangle can be less than 180, but they can't be greater. They are always less than or equal to 180 in measure.